let's get started. How's everyone doing? That was a very good, nice, heavy pasta lunch, so I hope we don't fall asleep in this nice, warm afternoon. To get things started, my name is Aish. I am an engineer. I work for a company called PagerDuty. We're based primarily out of San Francisco with offices in Toronto, Seattle, London, Sydney, and elsewhere, but I'm not here to pitch about my company or any of that. I'm here to talk about, as you can see in the title, building an SLA and tracking tool with Elixir and OTP. So before we get started, I actually got some questions about why is the title different from the original one that's posted outside or on the app. So let's actually get deeper into that. Why are we here? So before we get into the nitty-gritty details of this talk and what this talk is all about, to get some things out of the way, the term service level indicator is actually something that was coined perhaps within Google. So it's been something that has been popularized by the Google's SRE book. To quote them, the service level indicator is actually a carefully defined quantitative measure of some aspect of the level of service that is provided. So it's essentially a metric that gets tracked to show that whether your service or the software that you are building is up to the mark, whether it's running, whether it's dead, alive, it's fast, slow. So it's a quantitative measure of that particular thing. And this is usually carefully chosen when you define your system. So at PagerDuty, because we love metrics, we love monitoring, we love alerting, we actively keep track of these things. But if you're an engineer, you'd probably come back to me with this next thing. And geniuses on Hacker News have probably mentioned this a couple of bazillion times. Never build your own monitoring. Why is this even a talk then? Why am I here on stage trying to say that, oh yeah, we actually built our own SLI tracker, and here, this is how we use Elixir to do this? That's because, here's probably like another quote from Hacker News. That's why. That's because a lot of times, things in software are about trade-offs, and a lot of times, these trade-offs require you to do some things which are probably not always recommended. That's because there's always some sort of special cases, and in order to justify those special cases, I'm going to take you on a tour, a 3 to 4 chapter tour about what exactly was the problem that PagerDuty was facing, how we got rid of a legacy technical architecture, replaced it with an Elixir and OTP-powered asynchronous, event-driven, all those nice buzzwords thrown together architecture, and how at the end of this talk, maybe spend like the 10-minute part in actually going down what was the SLI that we're trying to track and how like the OTP is particularly like ETS table-based approach suited us. And disclaimer, if it worked for us, it is not necessary that it's going to work for you. So with that disclaimer aside, let's get started. So chapter 1, the problem. What exactly was the thing that we're trying to build? What was the problem that we're trying to solve? Before we do that, let's take a step back and think about the last time that you had an opportunity to build a solution for a problem. How many of us here have started by feeling that, with the feeling that the first step to solution is to the first step to solve the problem is to get rid of whatever is like pre-existing software and rewrite the entire thing. So to paraphrase, how many of you here have thought that rewriting the solution is rewriting the thing is a better solution? So I see like around, let's say give or take 15 to 20% of hands up. That's interesting because like that means 80% of you feel that rewriting is not a solution. So part of this chapter 1, the problem is about rewriting. So, and in order to rewrite, you need to have something in place first. So this is PagerDuty, or like part of what we call the PagerDuty's notification pipeline. So to those of us who are not employed by my employer, here's what this thing does. So at PagerDuty, the system here, shown on the nice chart on your right and left, what it does is that it takes an incoming record, which is a set of customer data. There's a system called an enqueuer that enqueues it into our legacy Cassandra data store. There is another system that actually pulls from this enqueued Cassandra store, sends it to a preprocessor that adds some sort of metadata, does some sort of validations, discards that enqueued data if it's not good enough, and then by calling a REST API, it sends it to a further downstream processor. So if you look at it, there is like a sort of an enqueue dequeue mechanism involved. So data comes in, it gets enqueued, it gets enriched, it gets thrown at an API, and the API does some sort of like final processing. So the problem that we're trying to solve and this was in 2014, so this was 4 years ago, the problem that we were trying to solve was to see how many of those entities were being processed. So how many of those incoming records were being processed end to end. So this is, give or take, the end-to-end throughput of the system. So per minute, per second, what's the number of records that is actually being processed? Sounds like a pretty trivial problem. Well, complexity is the name of the game here. So it was not really easy because the Cassandra pool that you see there and the incoming record that comes in was being stored in this custom, in-house, distributed task queue that was built using Cassandra. And because of that, it was not really easy for us to get the numbers right. So in order to answer this one question, how many of these entities were actually being processed, as well as the another important question, was the processing speed fast enough? Did we actually manage to get all the data that was coming in, do some sort of enrichment, and get the data out? We were trying to come up with some sort of solution. So the answer to this question could have been that, yeah, we are processing some of these things, we are not processing any of them, or maybe we're just processing like a part of them. So in true like metric-driven development fashion, what we did was we tried to come up with a scrappy little solution that worked at that time. So this solution, by no definition, was a complete one. So as you can see in the background picture, that's pretty much how the solution was like. So yeah, this is the same picture as 5 minutes ago. This is how the world was in 2014. But before we kind of get into the nitty-gritty of the next solution that was implemented in 2015, let me tell you a fun fact about this. The fun fact about this system was because this was using the queue that was getting enqueued into, so that the data was coming in and the data was being written into a data store. The data store was not really a queue. So unlike getting the data enqueued into something like Kafka or getting that data enqueued into something like SQS, what was happening was that the data was being enqueued, written into a database. And the database here was Cassandra. So it was a synchronously replicated cross-data center, highly available Cassandra cluster that spanned 3 data centers and took very little amount of time for a lot of writes that it was doing. And because of this, we were able to easily query the data, because it's a data store, and go and see what exactly came in at what point of time. I hope we all know how querying in Cassandra works here. So with that in mind, what we built in 2015 was this. So this is the old scrappy car that I showed you a minute ago. So what's going on in this picture? If you look at it carefully, and I mean really carefully, you'll see that there's another blob, another blue box towards the bottom of the picture. And what the box is doing is something quite simple. It's querying Cassandra. It's also querying the data from the processor. And it's trying to see how many records were processed. So all in all, what this solution is actually doing is that it's making a query to a database, the first one being Cassandra, because that's where the data was being enqueued. And once it queries that record, it's trying to make a RESTful call to the processor. So a bit of background about what the processor is doing. So the processor is this RESTful API written in Ruby that's backed by a MySQL database. So every time the metric processor tries to know how many of them were actually being processed by the processor, it first queries Cassandra with those same entities. Now it gives an input to the processor, and the processor says, here, 50 out of these 100, or like X out of these Y records are being processed. And taking this metric over time, we are coming at that metric. So this is like our first version, back in 2015, how the service level indicator for this end-to-end data processing system was being figured out. How was it? If you may ask me, like, how was the performance? Did it scale? Did it work? Most importantly, what was it? You might be curious. Was it something in Elixir that we wrote back then? Was it something else? Well, like I said, it was not the best thing. So what was it? It was this handcrafted custom script, or rather I should say a series of handcrafted custom scripts. A few shell scripts here, a few Python scripts there, a few Ruby ones there, that all did this one thing together. If they all ran at the same time, which means like first they were being scheduled, and then once they were scheduled, the input of one was being passed through some piping or through some temp files into another. But at the end of the day, they all worked. Or maybe like they tried to work. And what it did internally is actually here. So this is how the processing happened. So at a high level, the metrics processor was getting run every few seconds, and it was polling the Cassandra through an RPC call. Cassandra supports RPC call through Thrift, or at least the version of Cassandra that we were running supported it. And it was also now querying the processor. So most of the time it worked. So most of the time the 4 or 5 scripts that made the metrics processor actually worked, and the metric actually showed up in our actual metric reporting platform, which is essentially StatsD. But what does this mean? Like, if that worked, what's this talk about? Why are we talking about this at ElixirConf? This is not like shell script con. So that's because this design, as most of you kind of have maybe already seen this elsewhere, there's like a few problems. There's like a few obvious problems that one should not be doing. The first one was we are polling our Cassandra queue. We're polling the same database to which customer data was being written at a very high rate. And while Cassandra does support high write rate and high-ish read rate, we're also doing something that was not really recommended. What we were doing was we're polling our processor's RESTful API in the DB. So if you go a few slides back in here, you'll see that the processor's database was being polled all the time. So because of that, with additional load, things got really bad. How bad, you may ask me. So now imagine a lot of customers sending you a lot of data. So it's a lot of customers times a lot of data, and you're sending it to this RESTful API, which is written in Ruby, and it's doing this one thing, and it's writing it to MySQL. At the same time, every few seconds, there's another set of this family of processes, and these are like Unix processes because they are shell scripts and Python scripts and Ruby scripts that are trying to talk to the same API. Not the poor Ruby API. It now needs to multiplex between sending the data for the SLA metrics and between processing the data, the actual thing that it's supposed to do. With additional load, we actually made the problem worse. So the problem was exacerbated several times, and we really did not have any way of getting out of the solution. So this was end of 2015. So more or less, our SLI monitoring was making our end-to-end platform performance slower and less reliable because we were trying to poll our ultimate source of truth, the main relational database, for something that was not really important to us, or maybe not as much important to us. Enter chapter 3. So before I start talking about the part where Elixir actually enters this nice little story, something else happened in PagerDuty. And I have to tell you this tangential story, but trust me, these stories will converge. So what we did was, as a part of our architecture rehaul, and this is like a separate talk of its own, what we did was we replaced the Cassandra-based in-house distributed task scheduler queue with Kafka. And why Kafka, what was the distributed Cassandra-based in-house queue, is a different talk, like I said. So yeah, more or less, we replaced that with Kafka. And you might ask me, what exactly was the reason behind that? Why was Kafka chosen, and what exactly led to the demise of Cassandra? The simpler answer to that would be we chose simplicity over complexity. And to quote one of my favorite papers out of the tar pit, complexity is the root cause of vast majority of problems in software today. So in order to get rid of our problems, or at least minimize our problems, we decided to move out of Cassandra and into Kafka. So this meant, now this is where the stories actually converge. This meant at the end of 2017, so fast forward 2 years from 2015, this is how state of world of data processing at PagerDuty looked like. So again, on your left, there is some data coming in. It's getting enqueued by the enqueuer, and unlike before, the enqueuer is actually not writing the data into Cassandra. It's enqueuing these records into a Kafka topic, or like one or more Kafka topics, to be correct there. What's happening next is there's another process, which is the preprocessor, which is a Kafka consumer, that is reading this data from Kafka, and it's still sending it to the REST API. The only thing that happened here is that the Cassandra poll was replaced by the Kafka poll. Those of us who are familiar with how Kafka works might have seen what actually happened in here. This meant that a few things changed in this pipeline. The RPC-based lookups that our script was doing, the original script that was trying to poll Cassandra through Thrift RPC, that could no longer do so, because Kafka does not really provide a Thrift-based RPC mechanism. So the only way of reading from Kafka is to read from the log, because the log is the ultimate source of truth. So we had to ultimately resort to reading from the log instead of querying Cassandra for this time-sliced data. Also, processing the database was off the table. No, there was no technical limitation. We could have still polled the Ruby app, but why would we? Because 3 years ago or 2 years ago, with the old design, since we are making processing worse, we decided to move out of that anti-pattern. So with this new state of world in 2017, we were now facing the same problem as 2 years ago, but we are now determined to solve it in a different way. Even more importantly, as the company had grown and the throughput had grown and the amount of data had grown, we needed a better and a newer way of measuring the processing status and the processing strategy. So how frequently were these records being processed? How many of them were being dropped? How many of them were bad? How many of them were not getting enqueued? So all of that metric somehow needed to show up. So that was, again, problem definition V2. So this is where we actually bring in Elixir into the picture. But the first approach does not really involve the use of Elixir OTP like we intended to. So the first approach was more or less a prototypical approach, and we'll see why it failed and what went wrong, and we'll look at the newer approach next. So the first approach was, well, we had a relational database. We had a non-relational database. What if we take all the data and throw it in ElasticSearch and we start querying it? Because why not? ElasticSearch is something that we all were familiar with. It was something that supported querying things based on timestamps, slightly different from Cassandra, but still pretty much out of the box. And we could just like throw some Elixir client elastics in there and then just like query the data from ElasticSearch. What could go wrong? And the underlying motivation was, rather than querying the state in 2 places, we decided to query it in one single place. Was it a good idea? Definitely not. So this is what we ended up building. We built a pipeline to send the records and their state to a downstream data store, which was ElasticSearch. So this is how approach 1 looked like. So this is still 2017, by the way. And the data flow happens from your left, where there's this thing called incoming records. So the incoming records were being now written into Apache Kafka, and so were the process records. So unlike where the processor was initially being polled, so the Ruby-based processor was now writing the data about the incoming, about the processed events into Kafka. So these were like separate Kafka topics. It does say Kafka in there, but these are like separate Kafka topics or a bunch of Kafka topics. And from Kafka, there is this Phoenix app with some Broad, which is an Erlang-based Kafka consumer library. We were using Broad. So there were these Broad-based subscribers that were now polling Kafka for that data, and it was throwing this data into ElasticSearch. The Phoenix app is actually not exactly a Phoenix app. So I lied when I said that's a Phoenix app. It's an umbrella app which had an admin UI as a Phoenix app. There was another part of the umbrella, which is actually a metric aggregator. What the metric aggregator did was every some seconds, I cannot really say how many seconds because I don't really remember the number, but every few seconds it pulled ElasticSearch for the data using Elastics, got the numbers, parsed the metrics, and threw it to Datadog, which is like our metrics collector. And the other app, the other app, which is what I said was the Broad-based consumer app, was the one that was actually getting the data from Kafka, parsing the records, doing some sort of transformations there, adding some metadata in there, and throwing it to Elasticsearch. So there is like an umbrella composing of a Phoenix app for an admin UI, because who does not love UIs, right? And two other apps, one of them sending the metrics to a metrics collector, and another one of them polling Elasticsearch. How did this look? Did this look like something that worked? Initially, we thought, and when we built this project, our team was fairly new to Elixir. This was one of the first few projects that we built. And since then, we have done quite a bit of work. And we thought that this approach might actually work. Things were concurrent, things were fast, and with like supervision-based things, even if like the consumer were crashing, we could like restart, all those nice things. This was much better than 2 years ago or 3 years ago when we had those hodgepodge of scripts that had to be scheduled manually through cron, or had to be written in this custom way so that if one of them fails, another one of them should also fail. So this was much better. But did this solve our problem? Actually, no. The answer is no, this did not really solve our problem. This was because it was okay until we had one small problem. And the small problem was that the system crumbled pretty poorly when the load increased. So when the load went up by, let's say, 10 to 15 times, because we are polling our data store, yes, we are polling a different data store, we're not polling the production data store, but the system kind of crumbled. So this is what we had essentially done. We had just moved polling from one data store to polling from another data store. We had replaced Cassandra with Kafka. We had replaced those variety of shell scripts with this nice umbrella app, built a UI on top of it. But at the end of the day, the actual metric processing, the actual metric aggregation, was still relying on a stateful data store. And we, as engineers, took a step back. We started thinking about it quite hard, that is there a better way of doing things? Is there a better way of storing this data not elsewhere on a data store? Because if you store it in a data store, this is most likely going to be a poll-based action. Is there a way to do things in memory? Is there a way to do things in an event-driven way? So that led us to approach 2, which is more or less a variant of how things are right now. So which I call ETS all streams. And this is kind of a giveaway about how we did things. So before I kind of dive into this particular part, I wanted to know how many of us here are familiar with the term event sourcing or CQRS? Show of hands, please. So this is like around 50%, 60%, I'd say. That's quite nice, because a lot of concepts that we implemented were from event sourcing CQRS, not necessarily all of them, but these events were kind of sourced. So first, all of our records were events. All of the data that we are talking about, like, oh, the thing actually processed, or the thing actually failed, or something happened to something else, a customer's data came into the system, these were all actually events. So processed event record was an incoming event with some additional metadata. So what does this mean? This means that we were talking about the time when we processed customers' data, or the time where we said that, oh, this customer's data took so much longer because of something else. These were all stateful changes to the original state that had come in from the customer itself. So the data was simply the same thing with some additional metadata. And those additional metadata were simply mapped as like event changes. And the best part was, all the events were streams, or actually, to be technically correct, all these events were part of a distributed transaction log, and that was being stored in this nice little distributed log store called Kafka. So all of our events were already in Kafka. All the data was already events. So if you try to put 2 and 2 together here, the solution, which is like the crux of this entire 30-minute talk, is in this one slide. Diff 2 streams. What does this mean? Like, how do you diff streams? Well, here's like a very high-level, 40,000 feet view of the system. I hope I'm able to justify all the engineers. I can see one of my coworkers smiling at me from the back. So this is what we ended up doing. So if you remember the slide that I showed you like 10 minutes ago, you kind of remember that there was an umbrella app there. There's still an umbrella app there, but there's no Elasticsearch. What you see there is ETS. So here's what we did. So here, what we ended up doing was, rather than having the data stored in Elasticsearch and us pulling the data every some seconds or so, what if we store everything in memory? What if we store everything in memory in such a way that even if things crash, we can always reset the data from Kafka's offset? Which means because our entire set of data was events, what if we took events from two different streams? So there's one stream of things, which is just the data just coming in. There's one stream of things, which is just the data which is processed. Now, what if we try to merge these two streams and merge them in memory by using ETS? So ETS would now act as this temporary cache layer where we would get stream data from one of the Kafka topics, or like one set of topics, would get data from another set of topics. And based on the stateful changes, we would know that which original event had mapped into which of its future states. And based on that, we could emit a metric and say, oh, this is how long it took for this event, for this particular state transition to happen. Of course, we are relying on the system clocks and things like that, but this is not a distributed systems talk. So we were relying on the timestamp of the process and the incoming things and emitting these metrics outside. So as a result of this, there was no network calls being made. There was no sort of polling happening. Everything was being done in memory, where an ETS table was being written by multiple set of Kafka consumers, and another supervising process was responsible for emitting those, like checking whether those things are valid or not, and then writing the data for the downstream. You might ask us, why did we do it? Weren't there any other better solutions? Weren't there anything off the shelf? Couldn't this have been done in these 5 other different ways? Of course, but the reason that we went with this particular solution was because it was simple. It was not as complex. And also because memory access is thousands of times faster than random disk accesses. And that too, more than 1,000 times faster when you don't have to do it over a network or querying any sort of data store. So it was very fast as compared to the original solution. Also, modeling the data in its natural form as events was far more intuitive, which meant that the system was highly scalable, resilient, because we could always replay those events off of the Kafka log. And in the event the consumers crash or the data crashes or the entire supervision tree blows up, it could always restart, reconsume, and reprocess those things and keep those things in memory. And based on that, it could re-emit those metrics. Most importantly, one of those requirements that might have been hidden from us so far was that we only wanted the processing status for events in a window. There was no point of storing this data in Elasticsearch or elsewhere because the amount of data that we wanted was just the set of things that happened in the last like 4 to 5 minutes. So therefore, this solution actually made sense. As a result, this is where the part that goes back into the title of this talk. If you all saw this carefully, our system had fewer moving parts. It was simpler, and simple is beautiful indeed. Epilogue. How are things right now? Does PagerDuty still use this thing? Because this architecture is probably from 2017. We are like 9 months into 2018. How things have changed? Things have changed more or less. So here's an example how we deal with crashes. Right now, we are still trying to figure out how to figure out the right Kafka offset if things actually crash and burn. So right now, the solution that we take is actually we page someone because we are PagerDuty. We page one of our engineers, and the on-call goes in and sees, okay, the app actually crashed, and while reading the records from 2 streams, one of the records might have been like missing because something might have just gone wrong. In that case, it's a manual human action. But this is something that we have been thinking about, trying to recreate state from Kafka all the way, because we could always go back certain time in offset, and having another app sort of supervise this thing and trying to recreate the entire thing from Kafka. Another thing that we do currently is we also reconcile with a secondary data store. So if you remember that slide when I removed that ElasticSearch database, that was actually a lie. That still exists. But it's a background thing that just gets very temporary amount of data. And we reconcile with that if necessary. So the human engineer that gets paged goes in and tries to hit a button that says reconcile things. So the Phoenix app still exists. And what ends up happening is that by luck or hope, because these are like separate apps being separately supervised, the data most likely ends up in Elasticsearch, and we end up getting the right metric. And at the end of the day, if stuff still breaks, we get paged. Thank you, everyone. My name is Aish, and PagerDuty is hiring. So if you want to work for PagerDuty, please come find me. We're hiring everywhere in North America. Thanks. Also, I'd be happy to take questions now.
So I don't want this to be a why didn't you do it this way sort of question. I'm just curious from a functional perspective, were there specific features that you needed in your system that prevented you from exploring like K-tables or K-streams or some of the Kafka native stuff with windowing and joins and all that and aggregations?
So we did initially look at a few options which came with Kafka out of the box. The reason that we went with this one was we already had a system in place, and we decided to go with something that required the minimal amount of change, because the fundamental data structure, the fundamental store that we're using it's just ETS, and it's just a bunch of Kafka consumers doing, in the functional programming world, it's essentially doing like a zip width. It's doing a zip width on 2 streams. So yeah. Gentleman in the back.
Can you talk about the volume you had a bit of data that you're gathering for 5 minutes, and how you dealt also, if you had multiple nodes for the metrics, how you dealt with it with ETS?
That's a very good question. So first of all, because the data can, I think we store data for around less than 5 minutes. I think the mean data storage time is closer to a minute and a half or 2. We can actually store the data in a single node. It's quite a beefy node. It's quite bulky. So, but yeah, we can store that entire thing in memory. Also, that data gets lazily cleaned up, because when we get like the corresponding final state transitioned event, the first state gets cleaned from there. So does the next one. So that way, the size of the ETS table is always maintained. We also have other set of like actual monitoring, not the SLI one, because the SLI is like a business metric that is kind of visible to everyone in the team. There's also other set of like regular monitoring around the entire app through our container infrastructure or through our overall like just regular monitoring setup.
Yeah. How many events, like when you're under serious load, how many events do you drop generally? Like, are you dropping anything anymore, or are you pretty reliably getting through everything even under serious load?
So that's a very good question. So to get things out of the way, we don't drop any events. So in the core pipeline, no event is dropped, and on the metrics pipeline, which is the stuff that I showed it to you. So currently, we account for every single data that comes in. If anything, if we don't get a corresponding state transition, so if an incoming set of record comes in, and if we don't really get the corresponding outgoing set of transition state, within like maybe it's a 5 or 10 minute window, someone ends up getting paged. So we have like additional monitoring around like, okay, something came in, but nothing went out. So yeah, someone should be going in there and manually like reconciling it with ElasticSearch, or just going and like grepping through logs and looking at our other monitoring tools.
I just had a couple of questions about using ETS and how well it worked out for you. It sounds like it worked out pretty well, but one of the things I was wondering about was if you had multiple ETS tables across nodes, or if you just had like one node in which you were storing everything. If that wasn't part of your architecture, then no problem. And my other question is, did you have to do anything specific to prevent any of the ETS data from ever being paged out to disk? Because I noticed one of the things you said was you specifically wanted to make sure everything was hot in memory all the time.
Yeah. So that's, I think, something that we did consider. So initially, we did consider, so to answer that question in two parts. So first, we use a single node, a single heavy, beefy node. Part of it is because of our architecture in 2017. It's constantly evolving. So in 2018, maybe we should be able to use things like Erlang distribution and use like multiple nodes. But it's strictly like one actual like Beam node on like a Docker image that's being container orchestrated by an orchestrator runtime. And because of the versions of the orchestrator runtime, we could not attach our permanent storage. So because the container storage was kind of ephemeral, we could not have done anything that was disk-based. So it was part of it was because of technical limitation as well. But those limitations have now been solved. But because it's working and it's fast, we don't really have an incentive to do something else.
OK, great. Thank you very much.
No problem.
I was wondering if you could also talk a little bit about your Kafka cluster topology and whether you ended up with like partitions and if you're doing anything to like track offset lag at the Kafka layer with the consumers.
Yeah, we do have separate monitoring around Kafka consumer lags. This is done again through PagerDuty. Like my team, we operate like several Kafka clusters. And we have like a bunch of topics that is kind of dedicated to each and every like business specific role. And we have monitoring that does things like across these clusters. So we didn't really have to do anything in the app for particularly related to like consumer lag or Kafka health. But those are some things that the team has already done elsewhere.
Did you have to do anything in particular around memory back pressure if you are getting a large number of events in, and the processor is too slow to evict the original events from the ETS table? Is it just like, oh no, we've run out of memory, page someone?
Yeah, pretty much that. Pretty much, it's like the container orchestrator runtime saying, oh, looks like this container is like running low on memory. So that would get restarted and someone would be getting paged, oh, this happened like 4 times in the last 1 minute. Why is the supervision tree just like dying out entirely? Any other questions? Okay, I think we're done. Yeah. Thank you everyone for attending. And once again to mention, PagerDuty is hiring. Thank you.